Hello, everyone. How are you all? So, we are very glad to have you in our first webinar of the new year today from the Mashurul Hoque Foundation Winter Webinar Series. We wish you a very happy and healthy new year ahead. And as usual, we have come with another session today. So now in the beginning, we will start with a brief intro of our foundation. Our foundation, Mashurul Hoque, is a volunteer-enabled charity organization in Bangladesh. Our registration is in progress. We aim at providing support to the patient network struggling with a long-term illness, promoting their well-being in conjunction with the healthcare providers. We also intend to support and participate in research and education for the patient network. Experts are welcome, very welcome to join our initiatives and work together to build a healthy society. Today's webinar will be led by our guest speaker, Dr. Achille Salaun, who is an expert in data science, machine learning, and artificial intelligence technology. He received his PhD from the Polytechnic Institute of Paris in France. Achille is now actively working in clinical and healthcare research using AI technology. Dr. Salaun, now over to you.
So thank you very much for the introduction. Thank you also for the invitation. Today we will talk about survival analysis and more specifically about competing risks and multi-state models. So it will be much more about a technical presentation. And this presentation will actually be based on the paper called Tutorial in Biostatistics, Competing Risk and Multi-State Models, written by Putter, Hoque, and Geskus. So you don't need at all to have read this article, but it's just that it's a really good entry point to survival analysis. And I would like to share with you my reading about that paper. So to put some context about what I am currently doing as a project, I actually develop explainable machine learning models for clinical decision support in the context of kidney transplant offering. So the idea is the following, is that in organ transplant, actually organs are unfortunately a rare resource and patients have to register on a waiting list. When luckily, there are matched with a donor. Then an offer is sent to the surgeon in charge of the patient, and the surgeon has a choice to do. He needs to see if it's beneficial for the patient or not to accept the offer, or if instead it's preferable to wait for something better. Actually, my job is to provide tools to the surgeon to help him supporting that decision. In that case, we face a natural sub-problem, which is if the surgeon decides to accept the organ offer, then what would be the graft and patient survival outcomes? This question is actually a typical case of survival analysis. Survival analysis is simply the field that aims at predicting the time of occurrence of some event of interest. There are many cases of application. For example, we just talk about the prediction of graft outcomes. But for example, you could want to assess the risk of having cancer, for instance. And this application also goes far beyond the notion of healthcare. You can find it, for instance, in predictive maintenance, where you want to predict if a mechanical part will break or not. But let's stick to healthcare and more precisely to graft transplantation. Actually, over all this application, you can find many variants of the survival analysis problems. The most common variance implies the existence of covariates. So the occurrence of the event of interest actually depends on the characteristic of the subject. For example, in the case of the transplantation, it depends on the state of the patient. It depends on the characteristic of the organs. You also may face what is called censoring, which means that the state of your subject is not always observed over time. Sometimes you have some time window where you don't observe the patient, and the event of interest can still occur during this unobserved time window. Then you can have appearance of time dependencies. For example, the characteristic of the subjects may depend on time, making your prediction variable over time. And finally, among other variants, you can also have the case of multiple or competing risk when you are not interested into one single specific case of event, but several kinds of events. This is actually the variant we will try to explore today. So my presentation will be basically threefold. First, we will see how to formalize and define the problem of survival analysis in the case of one single risk. Then we will extend that problem to multiple risks, especially we will assume first that they are competing. And finally, we will generalize this problem to an even more generalized problem, which will relate to multi-states models. At the end of this talk, I will naturally summarize everything with a short conclusion. Sorry. So let's talk first about the single risk problem. Actually, its definition is pretty simple. It's simply to be able to predict when my event of interest will occur. In general, this problem is done in the present of censoring, which is basically the idea that the event, despite it is guaranteed to occur, may not be observed. For example, there is actually this really specific mindset in survival analysis where the graph will fail whatever the possibility. It's just that you need to give it the chance to observe it. So, for example, if the patient dies, for instance, unfortunately, there is still some kind of hypothetical timeline and scenario where we still can have a prediction for the graph failure. It's just that because of death, we had not the opportunity to observe graph failure. And there are actually several kinds of censoring. We will focus on the most common one, which is called rate censoring, which is basically the idea that after some time, the observation of the event is not possible anymore. It can be due to a variety of reasons. For example, a loss of follow-up because the patient died, because he left due to family reason, or because simply because of the end of study. That censoring data is, however, still relevant. Even if we didn't manage to accurately observe the event, we still have some information about it. Indeed, knowing when a subject has been rate censored tells us that the survival time, at least, is greater than the censoring time. So now let's provide a more mathematical definition of all this problem. Let's represent the survival time by a random variable t. Let's respectively represent the censoring time by a random variable c. We will assume they are independent. And actually, what we will observe is just the first thing that will occur between censoring and the event. So what we have, I don't know if you see, okay, you don't see. So what we observe is a pair with first the minimum time between the censoring time and the survival time, and the information whether it was related to censoring or to the event. So in practice, what we will have this kind of tables where each row corresponds to one patient, and then we have these pairs which are described in two columns. One column, so P actually stands for patient survival, because here we will first focus on patient survival, and then we'll have one column that corresponds to the minimum time between censoring and the occurrence time of my event, and whether it was if it was a censored event or actually the observed event. So it can be represented by this kind of graph, where, for example, my patient one here has been censored at some point. So what it means is that we know that death probably occurred, and it will occur after censorship. So we still have this information. And similarly, for patient 2 and 3, we have information here about the events. Now we have set up all our problem in a mathematical framework. What we want to do is actually perform survival analysis. So to do that, we need a key function to address our problem. Actually, the one we will focus on is the survival function, which is simply the probability that the event does not occur before a given time t. Here we have this probability of the event occurring after. This cannot be computed directly. Instead, we will use an intermediate function, which is called the hazard function. Basically, it tells you that given the fact the event has not been observed yet, so it's represented by this given t, capital T greater or equal than my little time t, it will tells you how likely is the event to occur soon after, where here we have a short time window that starts from time t. With this hazard function, we will sum over the whole period between 0 and t, and we will use that to derive the survival function. Therefore, the idea is that if we manage to compute the hazard function, we can compute the survival function and therefore answer to the question of survival analysis. So it's a good thing because we have tools to compute hazard function. In 1972, Cox actually proposed a model that, depending on covariates, so description of my patients, then Cox proposed a model of the hazard function. So this hazard function actually depends on the proportional hazard assumption, which basically states that the effect of covariates is actually constant over time. So we manage to split our model in two. One function, which is called a baseline hazard, which is only describing the hazard function from a temporal point of view, and then the effect of the covariates. Therefore, if you want to train that model, you can do it in two steps. First, you want to train the coefficient of your model by maximizing that partial likelihood. So I won't go too much into the mathematical details of that equation. What you can first notice is just that there is absolutely no notion of time in that likelihood, and it is thanks of the proportional assumption. And then in the second step, you can choose the baseline hazard independently, and you can estimate it with various tools, such as, for example, the Breslow estimator. So now you have at this point, you have a better idea about what is the survival analysis problem in the case of one single risk, and you are a little more familiar with at least one tool that can be used to address that problem. Now the question is, what if I don't have one single event of interest, but what if I have several types of events of interest? Then our problem is slightly different. We not only want to know when will the patient suffer from an event, but we will also want to know what will be the nature of that event. Here, you see that we have a really similar graph of compared to what we see previously. We still have censorship, but now we have various kind of events. Here, we will consider graft failure, for example, and the death of the patient. In addition, there is one thing which is very specific to the current problem, is that we are interested in knowing which one of event will occur first. So it means that we don't care at all about what will occur after, at least for this specific case. So it leads us to a redefinition of the problem of survival analysis in the single case. Here we have k types of events that are denoted by each event is denoted by a small k, and each event has its own time of occurrence. And the fact is, since we are in the assumption they are competing, what we see is not each of these time of occurrence, but we see only the minimum time of occurrence, and then we are kind of forgetful about all the other time of occurrence. We know they occur, we know they occur after, but we don't know exactly when. So finally, what we get is like the minimal time of occurrence for the associated event, which will be the first one to occur. When we add the notion of censorship, we find back something which is really similar to what we observe in the single risk case. Here we have the minimal time between the event occurrence time and the censoring time, and we have a description of the nature of what occurred. Is it censorship? In that case, we will have a 0. Or is it the event? And then in that case, we will have the k that corresponds to the first event which occurred. Somehow, you can see that case to some, you can see that notion of competition to some kind of rate censoring. Indeed, because you only see the first event, you don't see you don't observe the events after, and therefore you have the same idea that you have a partial information about the events that occur after. You don't know exactly when they occur, but you know they occur after. However, if you remember, there was in the single risk case that notion of independence, which is actually not the case anymore when you are considering competing risk. Indeed, for example, let's just consider these two following situations. In the case where you have some censoring, which is due to some loss of follow-up, for example, the patient decided to leave the study because he wanted to move from one country to another country, for example, for family reason. And this is not at all related to the state of the patient and therefore to the probability of having a graft failure or not. So it means that this loss of follow-up doesn't impact at all the time of occurrence of event graft failure. Instead, if the patient died and then death is a competing event with regard to graft failure, this will have clearly an impact on the occurrence of graft failure afterwards, because then we will know that the patient will not experience a graft failure. Therefore, that notion of dependence will introduce difficulties in the multiple risk case, such as bias. For example, the paper developed the case of another tool which is called the Kaplan-Meier estimator that doesn't rely on the notion of covariates. You will have lack of identifiability. So it means that some key functions that were computable in the single risk case are not computable anymore, and you will also face a lack of interpretability. So if you want to tackle the multiple risk case, intuitive solution would be simply to try to extend the notion of survival function. Then you would take simply the joint survival function, where you take all your possible kind of events, and for each you will want to know after what time each event may occur. So you have a time t1 for the first event, time t2 for a second event, and so on. And then you want to predict the occurrence of each event independently of the others. In particular, if you are more interested in one event, then you can just take the marginal distribution of that joint survival function by simply setting a 0 for all the events that are not interesting to you, and only considering your event of interest. However, due to this notion of dependencies and to this additional limitation, it has been shown. So you have here the reference if you want more details about it. It has been shown that these quantities are not identifiable from observation. In other words, you cannot compute them. However, and fortunately, you still can compute the cause-specific hazard function. And this means that if you cannot, despite you cannot compute the survival function, maybe with the cause-specific hazard function, you still can compute a quantity that will be useful and relevant to your analysis. So here, what is the cause-specific hazard function? It is almost the same formula than the hazard function. You have this idea that given the fact that nothing happened at a certain time t, what will be the likelihood of an event occurring soon after? And here it's not any kind of event, it's specific to an event of type here k. So how likely the event of type k is to occur after a short time after t. So with that, despite we cannot compute survival function, we can still try to apply all the relationships and all the function we derived in the single case. So these functions are not meaningful by themselves, even though they look like expression of what we observed during the single risk case. However, they are still useful because they allow us to compute another quantity, which is called the cumulative incidence function, based on that integral. And that cumulative incidence function actually is meaningful. It is simply the probability that an event of type k actually occurs before a certain time t. This is interesting because now, if we manage to compute the cause-specific hazard function, like we managed to compute the hazard function in the single risk case, we now have a quantity which is meaningful in terms of survival analysis. So another interesting point is the fact that if you are reading a paper about multiple risk, now you will understand why we don't talk about survival function, but everything is about cumulative incidence function. It is, for the example, the case of DeepIt, which is a deep learning tool that actually tried to derive directly the cumulative incidence function without considering cause-specific hazard function and so on. So this was more about a cultural point, but let's go back to our good old Cox model. Now, what we want is to compute the cause-specific hazard function in order to later have to derive the cumulative incidence function. What happens here is that for each cause, actually, we will have a proportional hazard model. So now we have like k different baseline hazard function, which are actually the baseline cause-specific hazard of cause k. And similarly, we will have k sets of covariate effects of cause k. Then, when you want to train each one of these models, it's like in the single risk case. It's just that you need to consider events that are not of cause case as censoring. This is interesting because now we still manage to perform survival analysis, however, it is at the cost of interpretability. In the single risk case, the coefficient betas had a really straightforward interpretation because we could relate their value, to the survival function. So it means that, for instance, if coefficient beta are related to one specific covariate, let's say, for example, the weight of the patient was high, then we knew that that covariate was important for the prediction because it would have a big effect on the survival function. However, if this coefficient was close to 0, then it would have no effects to the survival function, and therefore we knew that it was not really interesting, not really relevant to consider that covariate in our analysis. However, we cannot have the same kind of reasoning in the case of multiple risk. Indeed, now what we focus on is the cumulative incidence function. And that function is written like this. And in particular, in this writing, you have this function, which depends on two things. First, you have, so you have on the left part, yeah, I don't know if I don't think you see my mouse, so it's always a little more difficult to know exactly what I can show you or not. But you have this lambda k of s, which is actually the cause-specific hazard. So it depends on the covariate effects of cause k. But you also have this this function s, capital S, which depends on all the other covariate effects of all the other causes. So it means that in the cumulative incidence function, you have a big mix of both covariate effects which are related to the cause you are interested in, K, but also covariate effects that are not related to the cause you are considering. And therefore, the interpretation of the covariate effects with cause is much more difficult in the case of multiple risk. This consideration set apart, let's still try to generalize our problem by releasing the notion of competition. So now we will assume that not all events of interest are competing. And it makes sense because it's good to focus on the first event to occur, but it's also quite interesting to focus on all the events, not just the first one. And in addition, you can say that, yeah, past events may have an impact on the occurrence of the next one. For example, if I know that my patient experienced a graft failure or not, will highly impact my prediction regarding the death of the patient. So in practice, the data will be formalized like the table on the left. For each cause, so for example, here the J for will stand for graft failure, and the P will stand for patient death. So for each cause, you will have two columns. One column that describe the time of event, and one other column which describe whether that event has been observed or censored. So in that case, for example, the patient 1 has been censored for both events. In the patient 2 actually suffered from a graft failure after 1 year. So here the numbers are in days. So he suffered from graft failure after 1 day, after 1 year, sorry, but patient death has not been observed. So here we have the information about just the graft failure. And then there is this patient 3 who first suffered from a graft failure and then died. And then this can be represented by this kind of graph, where we have first graft failure and then we have the information about death. So it's interesting because now we are less interested in the occurrence of one single event, but more about what will be the path of my patient through a succession of states. In other words, we want to represent the transition from one state to another. And for that, there is a wonderful and really natural tool, which is graphs. So if we go back to the notion of competing risk, then actually it can be represented as follows. We have this initial state, which is the state alive, and then there are two possible outcomes. Either the patient suffers from graft failure, or the patient die. And then we see that graft failures and death are actually two competing risks. When we released that problem by allowing, for example, transition from graft failure to death, we actually have a different representation of what is possible to observe. We still have this initial state alive, and then there is two possible outcomes.
Hello.
Either the patient dies directly, or there is a graft failure. And from that graft failure, there is another possibility, which is death. In that case, graft failure is said to be an intermediate state. So in terms of vocabulary, you can also borrow vocabulary from Markov models. So then, for instance, an intermediate state will be called transient, and a final state will be called absorbing. In the paper, there is no specific requirement about the graph structure. However, they assume that the transitional graphs are actually directed acyclic, which is generally the kind of assumptions you like to work with because it's really comfortable. And in a situation where you actually have this notion of progress, it kind of makes sense. So with this graph of transition between states, then you still can go one step further, and that step is actually assuming that a multi-state model is a Markov model. In other words, the present state and the event, given the present state and the event history of the patient, then the next state to be visited and the time at which this will occur will actually only depend on the present state. So because you have this notion of both what is the state and what is the time at which I entry the state, there are several variations that are actually discussed in different papers. Anyway, I won't go too much into these details. Actually, there is a fun fact, is that a competing risk model is actually always Markovian, in the sense that since there is no event history, I mean, there is no reason to assume that notion of Markov model, because it's already is by design a Markov model. Additionally, the paper introduced a new format to tackle multi-state model. So on the left, we have the usual representation of a multiple risk survival analysis problem with 2 columns for per cause. And here the idea will be to expand that format into a format where each row actually corresponds to one transition with regard to one patient. So for example, here my patient 1 has been censored after 2 years. So there is 2 transitions to investigate. There is the so at time 0, my patient is alive. So we start from state A, which corresponds to alive. And there is this transition from A to G, which has not been observed. We know it's censored. And similarly, we do the same for the transition that goes from the state alive to patient death. For patient 2, we have a similar case. Here, there is a graft failure after 1 year, but no death, or at least the death is censored after 1 year. So what happens here is that we know that the transition from A to G have been observed, so there is a 1, but we don't have this observation for the transition from A to P, and that is normal. It's because the transition from A to G have already been observed, and therefore we got a 0 here. It will be a little more clear maybe for you with the third patient, where we have a little more interesting case, where we first have a graft failure and then the patient death. So what appears is that at time 0, we are in the state A. Then after 1 year, the transition from A to G, so from the state alive to graft failure, is actually observed. So we have a 1. Therefore, at this moment, we know that the transition from the state alive to patient death has not been observed and is censored. And then there is one transition left, which is starting after 1 year, because we know that 1 more year later, so after 2 years in total, then the transition from the graft failure to patient death will occur. This idea is that now, with all these different lines, we can turn actually a multi-state problem into several smaller computing risk problems with regard to transition. Indeed, we know that when the transition from alive to graft as is observed is actually competing with the fact that we will observe transition from the state alive to patient death, and so forth and so on. So now, if we want to perform survival analysis, everything is related once more about cause-specific, transition-specific hazard functions. So for each kind of transition, we will try to train a Cox proportional hazard model. And to do so, what we do is that we select only the relevant rows. The papers develop a little more how to do prediction with regard to this transition specific function. However, I won't go too much into details so that we can have the time for some question, and instead I will directly jump to the conclusion. So far we learned through, and with this, actually with this paper, and maybe with this, hopefully with this presentation, I hope we learn some key knowledge about survival analysis. We saw what is survival analysis, how it is defined from a mathematical point of view. We saw there was different kind of variants, what is censoring, and so forth and so on. We saw also more specifically how to formalize survival analysis in the case of multiple types of events. We even see the existence of a link between survival analysis and Markov model, which is actually the reason why I really like and appreciate to present that paper, because I think this idea is really exciting. And finally, we learn about how the lack of independence assumption actually can make things difficult, both in terms of bias, interpretability, and so forth and so on. However, this presentation is just a taster of that tutorial, and that tutorial is itself just an entry point towards in the field of survival analysis. The tutorial, so the paper actually focuses on Cox and Kaplan-Meier, which are classic tools, but more recent works have actually been proposed since, especially in competing risk. I would not be surprised about the fact that more recent works have been proposed in the case of multi-state models as well. This presentation is not exhaustive. If you have to take one, if you have to remember one thing, is that there are much more details in the paper, and that I hope it will at least have interested you to want to dig more into all these details and to learn more about survival analysis. It's time for me to thank you for your attention, and if you have questions, please feel free to ask them. I will be really happy to answer to them.
Thank you, Achille, for sharing such a useful information. I hope, like, who are working in such areas or interested, they might be, or maybe user group as well, might be interested to know more from you. So from our audience, like, we can ask, like, if you have any question, please feel free to pop it in the chat box, or you can unmute yourself, or if later on you can send your comments or questions via email or our social media page. So Achille, we don't have a lot of time left right now, but just a quick question, if you
Sure.
can give reply, like, how does this influence patient's treatment?
So in terms of
Is it
process,
clear?
okay, I will try and answer, and you will tell me if I got your question right or not. But so to have treatment effects, actually, you have to consider two scenarios. What happens if you do the treatment or if you do another treatment? In the case of graft transplant, it's what happens if I do the transplant or what happens if I don't do a transplant. And the question of survival analysis actually is to say, okay, let's say we choose that scenario, what would happen? And then you need to compare both branches basically. And so you will have two survival analysis problems if you have two different treatments, and you will compare these two results, and then you will take your decision.
Okay, thank you so much. Like, I asked this question from a layman point of view because I'm not expert in this area, but yeah, of course I understand that has important like that has importance in patients treatment and everything all. So thank you, Achille. If we yeah, thank you very much. I think any other comments and questions, I will request our audience to send us later on, and we will convey that to Achille.
Yeah, please feel to ask any question.
Okay, so today we came to the end of our session, and I will going to conclude. And thank you very much. And before saying goodbye, I'd like to remind you for our next webinar on 14th of January, next Saturday. So our guest speaker will be Professor Khandokar A. Mamun, will speak about building digital health ecosystem towards developed Bangladesh. So please register soon via the social media page and stay with us. Always keep well and take care of your surroundings. So good night and goodbye.
Goodbye, thank you.